So if you look at what you painted, in this upper left-hand corner we have the water. And you'll see this is where the color actually came out the brightest and darkest. What was over here, Reagan? This is baby oil. And do you see a significant change where we were painting with baby oil to where we didn't paint at all? Not really, right? It just looks kind of wettish or greasy. And then down here was this the isopropanol. Okay, so we saw some color start to come through in the lower left here with the isopropanol. And what was over here? The hexane, which the paper doesn't even look wet or change because the hexane was evaporating so quickly. So if we saw the most intense color with the water and the second intensity with the isopropanol, we saw no change with the hexane and just kind of a grease spot with the baby oil, but no significant color change. What does that tell you about the type of dye that's used in this product based on the polarity of the solvents that we were painting with? It's what? Polar, right? So it tells us that the dye is some kind of polar material. So this is a quick and dirty way to show that like dissolves like. Things that are alike dissolve in solvents that have the same polarity. So let's look at some examples on page 5-13 in your notes. Would you expect these solvents to be miscible with water or to dissolve in water? Methanol. Yes or no, class? Why? Why yes? Yes is correct. Because of the OH group, right? Because if we draw the Lewis structure for methanol, we have the CH3 and then OH. And remember, this is about that 105 degree bond angle, 109.5 squeezed down. So yes, we'd expect methanol to be polar. And we'd expect it to dissolve. How about this one? Would this dissolve in water? No, it doesn't. Why not? Because it's really very nonpolar. Okay? And I expect at this point in time you could figure that out by drawing out the Lewis structure and then looking at that. It's nonpolar. Does anybody know what this is? You ever take your clothes to the dry cleaners? No? Never? I do. I take my suits there, right? What does a dry cleaners do? Clean your clothes, yeah. They clean your clothes dryly without water. Okay? They clean your clothes without water. They use solvents that are not water because water will damage some of the fabrics. If you have silk, you don't take it and put it in the washing machine because it'll damage the fiber. So dry cleaning solvents are things similar to this. They are nonpolar solvents and they don't damage the fabrics, but they can soak out grease and oil stains and other things from your fabrics. Okay, how about this one? This is ethanol. That's what's in that Jack Daniels we were talking about earlier. So yes, and again, the polar hydroxyl group makes that dissolve. How about this one? What is this? It's not heptane, it's actually heptene, but would it be polar or nonpolar? Nonpolar because it's a hydrocarbon. So even if you don't recognize exactly its structure because it'll have multiple double bonds to only have 8 protons, it is a nonpolar hydrocarbon, so no. How about the next one? Here's ethane. No. And how about this one? It's kind of hard to tell at this point in Chem 101, but yes, it would be because of having all those oxygens in there. When you draw the structure out, you'll see some double bonded oxygens, and yes, it is polar. So sometimes as we're trying to predict whether or not things will be miscible, we have to look at the size of the molecule as well as its polar and nonpolar functional groups. Because if you get something that's really long chain hydrocarbon, say decanol, where you've got 10 carbons and then you have an OH at the end, the OH would make it want to dissolve in water, but there's so much big long tail of hydrocarbon that it's not very soluble in water. Okay, so there's a lot of things that affect solubility. So several factors can affect the solubility and the rate at which something dissolves. And the first one is temperature. Now, based on your everyday life from cooking, or anybody ever make that hard rock candy at Christmas where you throw the Lorraine oils in there? Okay, I like that stuff. So think about what you learned making hard rock candy. You start off with all that sugar in the pan and a little bit of water and the Karo syrup in there. What happens to the solubility of the sugar as you start cooking your candy? It goes up, right? So generally, temperature increases the solubility and the rate at which something dissolves. Most things dissolve better at high temperatures. There are a few bizarre exceptions, but we don't cover those in Chem 101. So temperature is the first thing that can help increase solubility. The next thing that can help is mixing. If you start stirring that sugary mixture, you can get it to dissolve faster. So mixing improves solubility. And the reason that it improves the solubility, when things will generally dissolve in each other. If two things are immiscible, mixing is not going to help. It'll just mix them up, and then when you let it sit, it'll separate again. Think old-fashioned Italian salad dressing, right? You take it, and you've got a water vinegar layer on the bottom and a greasy oil layer on the top with some spices floating around in there. And then you shake it up really hard, and you get tiny little droplets all mixed in each other, but as soon as you set it down on the table again, it separates, right? So mixing can improve the solubility because you have more collisions between the molecules and better interaction because you're shaking it up and mixing them. But if it's not going to dissolve in each other, then mixing it'll just sort of spread them around for the short term. And the other thing that improves solubility is the particle size. So smaller particles will dissolve better. And you know this again from your everyday life. If you take some sugar and you sprinkle it in your cup of coffee, it'll dissolve pretty quickly. But if you take a giant lump of sugar that's been sitting in the bottom of the sugar bin and put it in there, it'll drop down as a lump and it'll take a little more time for it to dissolve. So when we talk about solubility, we always are talking about the equilibrium concentration. And when we talk about equilibrium concentration, we're talking about taking a bunch of solid and just dumping it in a beaker and letting it sit there. And after time, some of it will be dissolving and some will actually be precipitating out at the same rate. So that's when we have equilibrium. We're going in both directions at the same rate. We don't talk about equilibrium a lot in here, but we talk about it more in Chem 111, and it's half of Chem 112. So unless you're going that route, you don't have to worry too much about equilibrium. But when we talk about this, we have three definitions: unsaturated, saturated, and supersaturated. Unsaturated means that we have less than the equilibrium concentration. So more can dissolve. Now, what does this look like to us, to our naked eye? Well, if I had 3 containers sitting there, and the first one is unsaturated, let's talk about just dissolving sugar in water. We're going to make some of that Lorraine oil candy. An unsaturated solution is just sitting there. I've put some sugar in there and stirred it up, and it all dissolved. And so what I see with my eyes is a clear, colorless solution. It just looks like water. But if I tried to drink it, it would be sweet tasting because there's sugar dissolved in there. So this is our unsaturated. Saturated means that we have the equilibrium concentration. So no more can dissolve at equilibrium. Now, can I make more dissolve? Yes. How do I do that? I heat it up. But at this temperature, at this time, no more can dissolve. And when we have this saturated solution, it means that we're at equilibrium. So what we see is we'll have solid sitting at the bottom of the beaker. We have solid sitting at the bottom of the beaker. So you can't see this with your eye, but what's happening on a molecular level is that some of this solid is going into solution, and at the same rate, you have material coming out of solution. You don't have the same amount of solid on the bottom and the same amount dissolved. It's the rate that is the same, not the amount. So it'd be like if I said, well, today I don't want to talk to 10 students that are here. I only want to talk to 8 students at a time. So 2 of you have to go out in the hall. And you can come back in when somebody else leaves. So if I put 2 students in the hall and I open 2 doors, as somebody's going out that door, someone can come in here. So I have 8 students in the room at all time and 2 students in the hall, and the rate of transfer is the same, but the number of students in the hall and in the room is not the same. Does that make sense? That's what's going on. It's the rate that's equal, not the amounts, and that's a common misconception. And then a supersaturated solution is really interesting. A supersaturated solution has more than the equilibrium concentration. Now, how do you get that? Well, you generally get that by heating the solution up, and then you cool it very, very carefully, and the material does not fall out of solution. But when you mistreat it in any way, if you drop a little seed crystal in here, I drop a little bit more in. They look like snowflakes, but they're seed crystals. Right now, the supersaturated and the unsaturated look the same. But if I drop this seed crystal in, all of a sudden, everything just precipitates. You just get solid dumping out. Have you ever seen those little instant heat packs? I forget what they call them. Reusable hand warmers, I think they're called. You can buy them in the sporting goods store. And it's a little plastic pouch that has liquid in it. And it has a silver disc that you click. And then you get precipitation and it gets hot because of the heat of solution or the heat